This screen is yours.
Yeah, thank you very much for the invitation and for the introduction. Is the sound good? Yeah, okay. For people in the room as well? Yeah, I guess it's all good. Good morning, everybody. I want to start with a disclaimer. I am a quantum chemist by background, and I saw a lot of beautiful, sophisticated chemistry in the previous talk. In my talk, I will essentially discuss tools and concepts, so the chemistry itself will be a little bit less sophisticated. And let me show you the team that work, and among all these people, there's a sub-team that is working in catalysis. And although we are originally and still a quantum chemical group by background, we initiated this project in catalysis a few years ago. And it was essentially motivated by the collaboration we had with some experimentalists. And in this context, we realized that what they were asking us to do and what we were doing was very much this kind of profile, energy profile that you're all familiar with. And this was for us a bit frustrating because we were always giving them a retrospective picture of what is going on rather than a prospective, and namely, the focus was on one specific catalyst with respect to few other, preventing us to get a bigger picture. So what we wanted to try to develop, it's more of a framework where we could say, okay, which catalyst would work best for a given reaction. And that's contained in this kind of framework that we call NaviCat, that contains several bubbles that you see here that are quite important because they target different aspects. But still, if you put all these things together, the overall goal is to be able to tell experimentally which catalyst is the most active or the most selective or the cheapest or the most abundant. And to do that with either a quite rapid large-scale screening or a reverse optimization, and I will come back to that later. And the component of this framework that I'm going to discuss today are what is listed here. And the first one, it's what I call the concept, and that's what will be the most important, I will say. And this concept will enable us to define in our research, using our strategy, which region in a landscape is the most active or the most selective. And once we have that, we can eventually accelerate the evaluation of the catalytic property using ML model, for instance, but also a multilinear regression. And once we have these two components, we can then plug that into an optimization pipeline and do a reverse design, which is, in a sense, the ultimate goal. So let me start with the concept, and that's the tool that we use to navigate the catalyst landscape. And a few years ago, we expanded the concept of volcano plot that is extremely popular in heterogeneous and electrocatalysis, and that is based on the underlying Sabatier principle. We expanded this concept to the field of homogeneous catalysis and extended the idea further so that it's better adapted for the problematic that we have in homogeneous catalysis. So here you see three different flavors. One is kind of a traditional so-called volcano plot. I will discuss that a little bit. The second is a two-dimensional version that we called activity or selectivity map. And the third, I won't discuss it today, but it's a data-driven version of those plots. And the reason why, as I told you, I will discuss a little bit how we build those plots in case you're not familiar with it. But what we like about it is that then with just one plot and one or two descriptors, we can immediately identify, you have here in the middle, for instance, the region that shows high catalytic performance or high, depending on the criteria you have. And this descriptor can then be coupled with a fast way to assess their value. And then we can put all this in a closed loop optimization. So that's what I will discuss. So just a few words on those plots that are based on the Sabatier principle, as I told you. I like to emphasize and insist that everything is a trade-off. It's always a trade-off. I think we saw also in the previous talk that for those directing group, you should find ways so that you don't have too much binding and it has to be well balanced too much, but not too weakly. So everything we do is always a trade-off. And this is also true, and you see it on the left-hand side with media. This is the US media chart where you have a descriptor, which is in this case, it's a biased. You have the target property that you're interested in, which is in this case, the reliability. And you see that some media are too much on the right, Fox News, some media are more on the left, that's CNN, sorry. And on the top, you have the most reliable media that have the least bias. So in catalysis, it's exactly the same thing. And that's something that Sabatier taught us. The best catalyst for a given reaction is the one that is going to balance the binding of the reactant and the release of the product. And this can be cast into those plots. I will very quickly tell you how they are constructed, where you have a descriptor that is easy to assess. And then you will have catalysts that are limited by the desorption of the product, so that those that bind too strongly on the left, those that bind too weakly and are limited by the activation of the reactant on the right, and the optimum region will be here on the top. So the question we asked ourselves a few years ago is, okay, if you think about a catalytic cycle in homogeneous catalysis, and here you have an example, very basic of CC cross-coupling, could you have the same reasoning, and could you think that, okay, maybe you will have some catalysts that will actually bind the substrate too weakly, and they will have problem then with the oxidative addition being limiting. You can have other type of catalysts that will bind the substrate too strongly, and then they will be limited by the reductive elimination that we see as a release of the product. And in the middle, you will have a kind of ideal catalyst that will be the Sabatier ideal that has each step requiring exactly the same energy. So not having one step that is very favored and the other one that is actually disfavored or the opposite. So if I want to translate this very simple picture into a more complete energy profile, what we would like to have for an ideal catalyst, and that's just so far a thermodynamic picture, will be the Sabatier ideal, where each step are equivalent. And here you see that you have a real silver phosphine catalyst that binds too weakly because the reductive elimination is actually too easy, but the oxidative addition is too endothermic. So the question is, can you kind of cast this idea and also have a volcano plot? And I will show you that we kind of obtain it. So how do we build those plots? Few words, sorry if you're familiar with it. In general, we take a handful of catalysts. We need a mechanism to start from, but the difference with the usual picture is that we kind of post-process this information in a kind of useful tools that enable us to rationalize what is going on. So we start with an energy profile where we can compute the delta G, so the energy of each intermediate with respect to a resting state. And the resting state could be the catalyst and the substrate that are separated. And we do that not for many, we do that for half a dozen catalysts. And then we verify that step B, if the delta G of each of these intermediate do correlate. And so far, and we have been building many of these plots, the correlation is always very strong. So if we observe a correlation, note that the scaling could be linear, but in principle, you could also have a different type of scaling. If you have a linear scaling in this case, then you can move to the next step and build those plots. And to build those plots, you choose one of the delta G as your descriptor, and you just express each of the reaction energy in function of this descriptor using linear expression. And at the end, you get this kind of plot that you see here. I just want to show you that the linear scaling relationship are quite strong and even robust. Here is different delta G of intermediate 2, intermediate 3 that you will have. And what you see here is that even if you change the ligation, that's an example with a metal and 2 ligands. Here is an example with a metal and 1 ligand in red, because sometimes we know that the ligation change, which means that the mechanism kind of change, but can still be covered by the same picture. Here is an example where you change the oxidation state, not only nickel 0, nickel 2, but nickel 1, nickel 3, and it still belongs to the same linear scaling relationship. And the last example is for theorists. Even if you change the spin, it's still in the same linear scaling relationship. So that just to show you that in general, they are quite robust, even if you modify to some extent the mechanism or the type of oxidation state that you will have. So that's the step is to check the linear scaling relationship. Then you can choose the descriptor and build this kind of volcano plate. And that's, I won't spend too much time on this one, but it's important. That was our first Suzuki Miura volcano attempt in 2015. And we were quite happy with it. And that's why we decided to push this story further. And why we were quite happy with it, because several aspects were in line with experiment, namely, here you have, it's a thermodynamic picture. Later on, you will see kinetics volcano, but here it means potential determinant step. So here you see that when you're in this region, you bind too strongly. So you have problem with the reductive elimination, and the type of metal and ligand that you have here is, for instance, typically nickel and platinum and amine ligand. On the opposite side, on the weak binding side, you have catalysts that are limited by the oxidative addition, so the binding of the substrate, silver, gold. And in the sweet spot here, you have palladium with phosphine. So this kind of good agreement, even in this limited thermodynamic picture, push us to continue and try to investigate how useful could be this concept to the field. And since then, we have built many different plots. We have also we have been addressing not only the scope of the catalyst, but also the scope of the substrate, which we know is very important. And I will show you a few examples on how they work in the context of this kind of closed loop optimization, how useful those tools can be. If you build those, you will realize that they are actually quite tedious to build by hand, even if it's very useful to learn how to do it. So for this reason, we are releasing an automated builder of this volcano plot. Here you kind of see an input file, and then you can generate a kinetic volcano, a turnover frequency volcano, or anything you want automatically. And we think it makes things much easier to provide this tool and to have this kind of a automated way to build it, because it takes quite a lot of time to build. So if you have this tool, you can actually spend time on the interesting science and not too much on the construction. So let me show what we can do once we have this plot. And the first example I picked here, it's a ligand optimization for aryl-ether cleavage, which is an important reaction, like many other reactions, but that's especially in the context of biomass degradation. And here we know that the mechanism is more or less what you have here, where if you cleave this other group, the catalyst that works well for that, even if it's a challenging reaction, is those kind of nickel catalyst with 2 ligands. And what we realize when building the volcano plot, so that's the result, it's the volcano plot that we have for this reaction. This is a tough volcano, meaning that this time you don't have the potential determinant step on the y-axis, but you have the turnover frequency, okay? And what we realize is that the meaning this time, it's not exactly binding the substrate too much or too weakly, because, I mean, it's not like in a cross coupling here. So the two sides have a very different meaning, which is not the case in electrocatalysis, where the meaning remains very consistent. But here what we observe is that we have the right-hand side, where usually you overbind, if I can say, the ligand, meaning that the intermediate with 2 ligands, like the intermediate 1 and intermediate 5, will be strongly favored, while on the left-hand side, it's more the intermediate that contain only 1 ligand that would be favored, namely intermediate 3, intermediate 4, and intermediate 2. So you have a competition between 2, 3, 4 on one side and 1 and 5 on the other side. So once you have this volcano, I told you that you can actually train model, whether you want to train a multilinear scaling relationship or a machine learning model, to predict the value of the delta G of intermediate 4, which is in this case our descriptor of any catalyst. And for that, I need to do a little parenthetic explanation on telling you which type of machine learning model we use in my group and which type of machine learning model are used in chemistry in general. This down here was just to show you that we can evolve from having a thermodynamic volcano, a kinetics volcano, and ultimately a turnover frequency volcano using this energy span model. But let me go back to the type of machine learning model that you use that will be very useful first for large-scale screening. And here in chemistry, there are different philosophies. You're probably very familiar with them. I could think of what IBM, for instance, is pushing, which is the natural language processing, which is very useful if you want to make a reaction prediction, but the input will be a string, so a text, and the output will also be a text. Then you have a second family of model, typically Matthew-Sigmund, for instance, which I call the pragmatic type of model, where your input will be any type of information that you know about your ligand, in the case of Matthew-Sigmund, or the catalyst, so any steric, structural, electronic information, and many more. And there you output very frequently is an experimental target, so the yield, the selectivity, the rate, or the turnover number. And as I told you at the beginning, we are quantum chemists. So when we do resolve the Schrödinger equation, in general, we only input the position of the atom and the charge of the nuclei. And that's why in the ML model that we want to use, we want to input exactly the same thing. So namely only XYZ geometry of an intermediate without necessarily having to optimize it. But we don't want to inject anything else, because that's how first principle people like to think, that minimum information should be sufficient to map the property that you are interested in. So that's this type of model that we have been training here. So again, to do the analogy with the Schrödinger equation, one molecule, you know the position and the type of atom that you're going to map with the molecular property of interest. You can do that by resolving the Schrödinger equation, but you can also bypass and building an Hamiltonian. That's what this H is kind of meaning. But you can bypass this expensive computation by training a machine learning model so that things become instantaneous. So with this philosophy, I'm going to give you an example. We have a catalyst here. Okay, it's not yet the one associated with the aryl-ether cleavage. That's just an example. And we are going to represent this molecule based on the atomic position and the charge of the nuclei. And to do that, we have to find a way to convert this kind of chemical information into a numerical form, or a vector if you want. And very frequently, we use quite simple expression. Here you have just a Coulomb repulsion, an expression that follows the Coulomb's law. And then we obtain some kind of vector. And with this vector, we can measure the similarity between the vector associated with a new compound and the vector associated with the molecule that were in the training set. And we measure the similarity between those using a kernel similarity function that you see here. And the bottom line is that at the end, we want to make a prediction that is the x-axis of this volcano, right, for a new catalyst M. And this prediction will be made by a sum of training instance, and every training instance get a weight that you obtain through the training of the model, and the weight is then scaled by this kernel similarity function, measuring this kind of similarity between a new catalyst and the catalyst that is in the training set. So a lot of effort in the field is actually placed in trying to find what is the best representation that you can use. So now, basically what I will have is that I will have a model that you inject an intermediate and you get the descriptor directly. So let's use it. And that's kind of the ML-based screening of this aryl-ether cleavage. And what is interesting to see, and it's very different from Suzuki cross-coupling, for instance, where you have a lot of catalysts that appear in the top of the volcano. Here, you clearly see a shift toward the right. And what you see here, these two Gaussian correspond to the occurrence of one given type of catalyst, and I come back to that later. But we screen 150 catalysts, 50,000 phosphine and 90,000 carbene. And the height here, see the count, so the occurrence that you have, depending on the value of the descriptor. And you see that you clearly have a shift toward the right. So what is happening here actually is that we are favoring too much binding the two ligands instead of binding only one ligand and something else. And those that chemically, I'm not saying it's chemically sound, but that's what we obtain in this case in the computer, that are able to reach the top of the volcano, are those that actually destabilize the 1 and 5, which were those intermediate with two ligands. Sorry, you have an example here, and they do stabilize the intermediate 2, 3, and 4 that were the one with only one ligand. And in this case, this stabilization is not really driven by the electronic. It's really driven by those kind of non-covalent interactions that might exist between the ligand. So that's the reason why there's so few ligands in the top zone. And that's why for this particular reaction, we haven't yet identified let's say the palladium phosphine equivalent of cross-coupling catalyst. So once you have, and you can see that one of these ligands that systematically come close to the top, not ligand, but substituent to the phosphine, are those pentachlorophenyl. So that's a high throughput screening, right? But you can do something else. You can also, if you have this kind of volcano at hand, you know the sweet spot. So you know where is your optimum region in terms of the descriptor. And if you know where is your optimum region, it means that you can build a fitness function, right? That is very natural, that define whether you're in the appropriate region or not. And you could use this fitness function in a optimization procedure. And that's what we have done here. So that's inverse design, right? This time, you know the target property, that's the top of the volcano. You have a fitness function because you have this tool. You want to know the optimum catalyst, and you want to optimize, the fitness function, right? And to do that very rapidly, you need, for instance, a machine learning model or a multilinear regression. So if you have all these ingredients together, you can do this inverse design optimization, and that's a tool. So I just want to see something that doesn't make necessarily much chemical sense. But here, the way we fragmented, you see that the different genes correspond to different substituents to the phosphine. And I know that having 3 different substituents, it's synthetically a little bit crazy, but 2 substituents you could actually evaluate, synthesize. But that leads to, if you assume that you can vary these 3 substituents per phosphine ligand, you could have up to 67 power 6 possibility. So that's why to evaluate all these possibility, you actually need a kind of smart way to optimize. So then you have this different chromosome, as they call. We usually have 10 chromosomes, so 10 ensemble of these 6 type of substituent per iteration. And that's where you need to quickly evaluate the fitness function, so this that connect to the volcano. And then you can have, of course, mutation and crossover and so on. And usually you will optimize, you will converge relatively fast. So I want to show you the result of this optimization. You see that at, oops, sorry, I'm doing some bad thing with my keyboard. You see that after 20 iterations already, 65 is identified as a good substituent that leads to the best possible value in this optimization. But you can play with the evolutionary experiment and say, okay, I'm not interested in 65 because 65 doesn't make sense experimentally. So let's remove 65. What comes next in my optimization? And here we saw, for instance, 48 and 66 coming next as a better substituent. And you could also ask another question, okay, which substituent leads to a systematically poor value of this volcano descriptor? So what is interesting is that that's the proof of principle that the genetic algorithm is working. So the fact that we converge again to 65 was actually very reassuring here. But the bottom line is that you have a quite versatile and efficient way to optimize. And I will show you in a few minutes that you can also, it's also applicable to a multi-objective function and applicable to other fitness functions. So far I showed you that you have this volcano, that you can use it as a fitness function, and that we have easily access to machine learning model that we use in quantum chemistry that inject the structure, but sometimes those machine learning models are not so adapted, the quantum one. Maybe the pragmatic approach will be good, but we can also improve our quantum-based machine learning model. And here is an example where they would not be very adapted. I told you before that what we map usually, it's one structure, one property. And this works quite well for this volcano x-axis that I showed you before. But if the property that you're trying to target is, for instance, an activation barrier that actually depends not on one geometry now, but on 2 intermediate, the one from before and the one from after, this mapping of one structure, mapping one property is going to be difficult if the property is complex. So in this case, it will actually work better to inject not only one molecule, but for instance, the intermediate before the transition state minus the geometry, approximate geometry of the intermediate after the transition state. And this is very relevant, for instance, if you want to try to use this kind of ML model to predict enantioselectivity, because those are very subtle property. So some ML advancement are needed if you want to learn challenging energetic properties, if you have sparse data, which is frequently the case in chemistry, and especially if you want to focus on reaction-based property, because in reaction, usually more than one geometry is actually relevant. So I'm showing you an example now how we could build this improved ML model for this situation. And for that, I want to consider an organocatalytic cycle to change a little bit from transition metal catalysis. So here you have a cycle for the propagylation of benzaldehyde, and the key enantiodetermining step is here. So you see that this transition state kind of resemble, correspond to an interpolation between intermediate 2 and intermediate 3. And the type of asymmetric ligand that have been tested here are those different scaffolds with different substituents. And here, of course, what we want to try to evaluate is the enantioselective excess that you can get from a delta, a difference between the activation barrier leading to the R product and the S product. So this is, of course, very difficult already from the DFT point of view, but from the ML point of view, mapping just one structure to this delta E is going to be also a challenge. So let's see what we can do to resolve this problem. And for that, I am going to use a slightly different expression of Z, Z, and R of my ML model, but the spirit is the same. So you have here different terms that use this information related to the 3D geometry and the type of nuclei, having one body, two body, three body terms, and this kind of expression will be transformed into a vector. But I don't need to really tell you more with that. So what you need to know now, look at it now, it's this right-hand side. So the right-hand side, you first have the DFT reference value that correspond to the EE computed with DFT. So of course it's challenging with DFT also, but I'm going to leave this challenge aside. And what you see here on the next to DFT is what you the prediction that you obtain by the ML model if you only use the intermediate two. And you see that it's not actually, the prediction are not very good. That's why you see a lot of red square here. Another way, more technical, to see that the prediction are not very good are those dissimilarity plots that we use ourselves to diagnose the accuracy of an ML model. And it's quite intuitive to look at it because we know that the ideal behavior should be that if you have two equal structure or catalysts, the target value should be the same. Meaning that if you have the distance between your two representations should be 0 for two identical structure, and the difference in the target value should also be 0. So the ideal behavior of this dissimilarity plot should be this kind of cone that you see here. They represent the ideal behavior because two equal structures should lead to the same target value. And when we take only one intermediate in our representation, we see that it's really not the case. So what we can do to improve is to find a way to incorporate two structures the same way we will do in chemistry, 3 minus 2, which is a kind of reaction. And you see that we improve already the dissimilarity plot and improve the mean absolute error of our ML model, which is also what you see here. We can even improve further by selecting the best feature afterward, and I won't insist too much on that, that match better with the target property. And by doing this final exercise, you see that you improve the behavior of your model, but also improve the prediction that you see here in the bottom. So I won't insist too much on the feature because it's not super relevant, but what I want to show you is that if you take this diff version of the ML model that use the different structure rather than only one, you also get a much more transferable model and can make prediction for scaffold that are not necessarily included in the training set. And here is a scaffold of, for instance, 7 that I didn't discuss before, but that has been shown experimentally to perform very well. So if I have a good ML model for the EE, so for the selectivity, which is the most challenging things to actually predict very quickly, I can then focus on the Pareto Front and try for the same reaction that you have here to build a volcano plot this time, to be able to have my fitness function for the activity. So this is, again, the TOF, and you see that it's a volcano plot that tells you which scaffold, and you see number 7 again here, that is this time not good for selectivity, but actually quite good for activity. And it's not surprising that everything is on one side of this volcano, because this side here is actually the side that corresponds to the enantiomer determining step, while the slab on the right here corresponds to the release of the product. So, which is not limiting in this case. So we have a way to evaluate the EE, and we have this volcano that gives us the fitness function for the activity. So what we can do now is that we can have an optimization of both activity and selectivity. And of course, it's quite challenging here because we can already see by the difference between these two lines that what is going to be more selective is probably going to be quite low in the volcano, so not the most active. But we run anyway the genetic optimization as before. This time, the fragmentation that we had were based on different backbone and or scaffold, if you want, and different substituent R1 and R2. So the combinatorial space that we covered was 14 scaffold times 34 substituents times 2, so it's also quite large. And again, we can build our different chromosome, do crossover and mutation, and select the criterion that we want to decide what do we want to prioritize, a bit more selectivity or a bit more activity, so you can play with the optimization. And that's the result of the evolutionary experiment that you have here, where actually it's not super good in terms of activity. To have something super good for activity, we should be very low, because the volcano value was actually quite low, as you can see it here in terms of this descriptor. But that's so far the best compromise, and this big jump comes really from identifying scaffold number 7 as offering the best compromise. I know I have only a few minutes left, so I want to discuss just one example very quickly, and then I will close, because all the thing I have showing you, it's not really related to experiment yet. So you will be very skeptical and asking me, why does it actually work? So we spend a lot of effort right now for the validation and the reality check with experimentalists. And here is, I think, a nice example where we develop those maps for selectivity and activity for a reaction that show competing outcome depending on the solvent. If you have TFE, you will have cyclopropanation, that's a CH activation type of reaction. If you have a methanol, you will have carboamination. And what we see here is that the map actually reproduces very well that with rhodium, if we are in TFE, we are much more selective blue for cyclopropanation. If we are in methanol, we are much more selective red for carboamination. And rhodium is really ideal for this solvent-induced reaction outcome, because you have good selectivity, good and distinct selectivity in the two solvents, and also very reasonable activity, that you see on the right plot. What we want, there are many things based on this map that we're trying to evaluate experimentally. One being that ethanol is not an innocent change. You might think that going from methanol to ethanol, nothing will be different. But actually, if you go to ethanol, you can see that with the same catalyst, the selectivity is much worse. That it's this kind of very light red region. And that's something that we try to evaluate experimentally, not us. That's our colleague, Nicola Kramer at EPFL. And you see that here exactly what we kind of predict. And that's just a demonstration that it does work, that the selectivity gets lower in ethanol than in methanol. And you have the opposite selectivity in TFE that you have in methanol. With this, I think I had other example, but I want to conclude here to eventually leave time for the question. And just briefly to wrap up, the concept that we use for everything are those kind of molecular volcano. If you have that, we can do many things with this. There's still a lot of limitation. We want to have a missing automated reaction mechanism prediction to do everything even faster. Automated building of structure and conformation. This is something that we're working on. And of course, we are aware that the reality is often more complex. That's why we need to validate what we do with experimentalists. And finally, let me thank all the group members who did the work that I presented to you today. Thank you very much.
computational tools that can help us to understand the catalysis. The talk is now open for discussion. We will start from the room here first. Yes, please.
I just wondered how you account for unwanted side reactions that lead to catalyst degradation. I wonder if that's one of the complications that you spoke about on your final bullet point. So it seemed like there are multi-dimensional volcano plots for all sorts of pathways that, for instance, lead to ligand degradation that reduce catalyst performance. How do you account for that?
It's kind of very difficult to hear. Sorry about that.
Can I try again? Is that clearer now?
I think it's better now. Yeah.
So what I was asking was, how do you account for, how do you incorporate catalyst degradation by unwanted side reactions? So not just modeling the pathway you want, but the pathways you don't want.
Yeah. That's a very good question. That's a challenge. That's one of the limitations. So the way we do it is that if you have a map, right, and that finally experimentally the product you get is the map will only map the reaction profile that you're looking at. There's no miracle here, but we can successively add more degradation pathway or competing a reaction to the map, but we have to self-consciously include them to have them in the picture. So we actually do that for the last one I showed. This is something we have been doing, but we need to do it, to be aware of it and to include it self-consciously. Otherwise, it's limited to what you plug in, what you input to it. So we are not yet at the stage where all the possible pathway will automatically be mapped. We need to think of, we need to consider them self-consciously.
Sorry, maybe quick supplementary question. So turnover frequency between these reactions, is that over a given time period? Is it over different time periods? Is it an initial rate? Is it a, because that, of course, reflects what I'm saying about degradation.
When we combine the map with microkinetic modeling, in principle, we will see what happened in time. It wasn't the case for the one I have shown, but in principle, you can add the time dimension and the effect of the concentration by plugging them with microkinetic modeling, which is something we have been also doing. So there are ways to make them as sophisticated as you want. The key being, are all the pathway investigated and taken into account? That's something that is a strong limitation.
Yeah, Richard, thank you.
Well, first, thanks for a very interesting, really fascinating talk. I think my question probably links to the previous one. You mentioned on your last slide that there was a kind of missing loop with reaction mechanism prediction. How are you proposing to get rid of that missing loop? Because I can see it really is important.
Yeah, it's super important because it's our starting point, right? So this is something where we need to put effort into. So there are two things that we're working on. First, it's not necessarily yet the reaction mechanism, but to be able to compute automatically all the intermediates that we know are relevant. And this is not going to be very difficult to do, and we're actually doing that. Then on this first step, I worked very closely with my Zurich colleague, Markus Reyer, who is involved in developing workflow for automated exploration of reaction mechanisms. So far, we left the burden on him to do that. And once he's done with that, we are in a big network together that's called the NCCR Catalysis. And he is supposed to then plug it in to what we do so that we can combine the two aspects together. So this is the effort made by Marcus Schreier, and together we are going to plug these two things in. It's a super difficult work that he's doing.
Thank you.
Thank you. Is anybody here? If not, then we will go to Josie. If you have any questions there,
we have
please.
Lots of questions. So Lara asks, how could she get a version of Navicat?
Yeah, so what is it's online. What is going to be released very soon is what is Navicat? Navicat is a combination of many tools. So it contains Volcanic, which is the automated builder for Volcano, and it contains this Navicat GA, which enable the optimization, and it contains many other tools that are released step by step. So Volcanic and Navicat GA are going to be released in January after review process, but that everything is going to be available in the Navicat link. But Navicat just combine all the tool that serves to do all this effort.
Okay, thank you. One more question, maybe. Josie, if you have any one more.
We have plenty online. I'll just go in order that they came in, to be fair. So Natalie Fay says that the mapping that you've done is very impressive, and thank you for sharing the software. She has she has two connected questions. Hopefully we can get through them both about the computational studies that underpin your post. Firstly, you rely on calculations for barriers, but there are problems with DFT which can make it very difficult to compare competing routes properly. As a simple example, the precursor of cross-coupling reactions can be an equilibrium between PDL3 and PDL2, with PDL4 and PDL possible for some ligands as well. Apologies if I've said those wrong. Assuming that PDL2 is your entry point, do you have any way of incorporating more complexity into your models? As mechanistic understanding involves? Yeah.
So there are many complicated aspects that I didn't disclose. And what is said here is completely true. What we realize is the best thing for us, it's when we go with the experimentalist and we realize that what we predict fails. And when this happens, is actually great for us, because then we add more complication in an iterative cycle. And I hope that we can gather more and more of this kind of failure and rectification to actually have this incorporated later in a more general and standard way. But we are far from having everything perfect with no problem.
And the second half of the question is, have you explored ways of capturing when the mechanism changes, especially when comparing different metal catalysts, or are you tied to a single mechanistic hypothesis in your models?
No, we did many different things. Like we are working, for instance, also the substrate scope. So what's happened when you change the substrate? What's happened when you change the solvent? We have example where the 2 dimensions correspond to 2 different pathways. That's kind of cool, one pathway. So we have plenty of dual hypotheses that can be mapped, or maybe more than 2 actually. So we are playing a lot with all these different possibilities. So I think there's still a lot of things to try.
Okay, I think thank you very much for that. We will stop it here. Then we will once again thank Clemence.
Thank you very much.